record here, yeah. All right. So to begin today, actually, let me give a quick comment about the tests, and then we'll jump right into the notes on acceleration. So for the tests, I've got a few more to grade, and then I have one student who was ill, who still needs to take the test. And then I have my international remote learning students. The school administration's arranging a proctoring session for them, and it's supposedly going to be sometime this week, but I don't know what day or what time. So as soon as the student who was ill and then those international students get caught up with the proctoring, then we'll start looking at the test in more detail. Right now, though, for your classes that are graded, you can, I think there's kind of a workaround where you can go into assignments and then find there's a button that says grade detail for your class or something, and you can see your score. It's not published, so you can't actually see your test and see my comments and see what you missed, but you could at least see your score. I think you can find a way to locate that for those that are finished. And in terms of what we'll do moving forward, the score that's posted is not curved yet. So that's just your original score before the curve. It won't be a full AP curve. So, you know, for an AP curve, you could get like a 45% and still pass with a C. But with the curve that you'll have on this one won't be quite that steep, but I need to get a few more data points in. It's not just a straight linear curve. It looks at the difficulty level of the questions, and it looks at the achievement of the students, and it creates actually a two-wave curve where part of it's a little bit linear and part of it's cubic, and it overlaps. And so I need more data before I feel confident with that curve. So, but once I get a few more inputted, then I'll put it into the spreadsheet and see what it kicks out. It won't be, like I said, because of the difficulty level of the questions, it won't be that real steep AP curve, but it'll be a curve. So when that curve is established, then I will change your grade from the current score to the curved score after you've completed your test corrections. And we'll probably start working on test corrections next week. Since I don't know exactly when those students will get that made up this week, I doubt if we'll get to corrections yet this week, so it'll probably be next week. And then after we do the test corrections, I give you the curved score as soon as you've finished those corrections. And then you have an opportunity, if you choose, to do a retake. So this is our first major test. So I just want to remind you of those details from the classroom management plan. So if you find your score and you did better than you expected, then hooray, your corrections will be brief and easy, and it'll even get better because the curve will come in. If you find your score and you did worse than you hoped, no need to panic. After corrections, you'll have a chance to earn the curve, which will give you a higher score. And then you'll also have the opportunity to do a retake if you choose. So that's all stuff we'll be working on next week. Any brief questions on the test before we jump into today's lesson? All right. So as I said, we're going to be talking about acceleration today. So let me jump right into the notes. For acceleration, go ahead and just put in the chat, what do you know about acceleration already? Definition, whatever. Anything that you think you know already about acceleration, what do you think it means? Just type something in the chat. Don't worry about if you're right or wrong. Just what do you think you know about acceleration? Increase, decrease of speed, how fast the speed changes, how fast something gains speed, increases velocity of an object over time, gaining speed, increasing of speed or velocity, the derivative of velocity, okay. All right, good. A lot of different thoughts at all kinds of different levels. Some of them precise and exactly the way I would define it. Others, maybe, I wouldn't say wrong, but maybe we could add a little bit more detail or add a little bit of a tweak to it. So what I always like to highlight here is that all of you have some sort of an understanding about what acceleration means. It's not something so foreign or something so new that it's sort of hard to comprehend. We'll tweak it, we'll define it a little more clearly as we go, but you already have some intuition about what it means. So let's jump in. Here is the definition. give you a few seconds to jot some things down and read it over. So you can see in the red words a really brief and yet accurate definition. Acceleration is the rate of change of velocity. Quite a few of you talked about objects speeding up, which would be one example. You could have an object slowing down, and that would still be an acceleration. In common language, we might refer to that as deceleration, but in physics, we don't really tend to use the word deceleration. We just talk about whether the acceleration is positive or negative. And then another form of acceleration, which probably most of you haven't really thought of before, is just changing direction. Because recall, velocity is a vector. So not only does it have a numerical value, a magnitude, it also has direction. And so if the definition of acceleration is a change in velocity, it could be that we're changing the actual magnitude, which would be the same as the speed, or it could be that we're changing the direction of the movement. So either of those examples would give us an acceleration of some sort. And then so you can see the equations here. Acceleration is delta v over delta t. And then the one to the right of that, delta v can be rewritten as vf minus vo. The change in velocity would just be final velocity minus initial. And then often we won't include that triangle, that delta symbol with time. Often you'll just see it listed as time, because when we measure it, we typically just use a stopwatch, and it normally will start at 0. And so whatever the stopwatch says at the end is not only the final time, it's also the elapsed time. So usually the final time and the elapsed time are the same thing. And so we typically, you'll see it often just written as t, not delta t. And then just in a word equation, acceleration is the change in velocity over elapsed time. So that is a pretty concise and abbreviated definition. We'll expand on different aspects of that throughout the semester. Any questions about that so far? Probably pretty straightforward. I don't think anything too shocking here. All right. As I mentioned a minute ago, acceleration is a vector. Since it's based on velocity, and velocity is a vector, therefore velocity has both numerical value and direction. If the velocity has a direction and the velocity is changing, then the acceleration must impact either the direction or the magnitude or both. So acceleration also will be a vector. It'll have a directional component to it. And then below that, you can see it says, since only constant acceleration will be considered in this course, we will not differentiate between average and instantaneous acceleration. So as we learned in our last unit, sometimes average velocity and instantaneous velocity are the same, and sometimes they're different. And technically, that's also true for acceleration. But for the concerns of this course, we'll only ever be thinking about constant acceleration scenarios. Now, it might be that in segment 1 of the movement, it has a certain acceleration. And then in segment 2 of the movement, it might have a different acceleration. But we'll break it into parts like that. We won't ever have one elapsed time frame where it's changing its acceleration within that time frame. If it changes its acceleration, we'll break it down into different time intervals. So to really analyze acceleration that's changing in a single time frame, we kind of need to use calculus to do that effectively. And so we're not going to go there since this is an algebra-based course. Now, another thing I want to highlight up at the top is if you look at the equation of v minus vo, you'll notice that there's no f on the velocity. And there sometimes, excuse me, I'm gonna wake the dog up, starting to snore. Sometimes you'll see that they'll leave the f off of that final velocity and just call it v for velocity. So just want to highlight that so that if you see a v minus vo, or if you just see an equation that has a v without an f on it, that you don't get confused by that. So just a quick point to make that highlight. The units for acceleration should be pretty easy to understand if we know the units for velocity are meters per second, and we know the units for time frame are seconds, then the units for acceleration should be meters per second, or meters per second squared. And I'll just type something in here for you. As you're having to type a lot of your work out these days with remote learning, you might want to just type it this way, meters per second. That is acceptable. It's not wrong to type it as meters per second over seconds like you can see up here. It's more common to see it as meters per second squared. But if you're typing it in and you don't want to mess with the little caret symbol, or you don't want to try to figure out superscripts or exponents, just this meters per second like this is also a good acceptable way to write it, and make it, so it's just easier to type, I think. So you can use that as well. Any questions about acceleration? That's it for the definition. Now we're just going to practice a couple problems before we move on to the next topic. All right. Hearing no questions, we'll keep moving. Acceleration is the rate of change of what? Go ahead and put it in the chat. Good. Seeing from almost everybody the selection D. It is the rate of change of velocity. We can confirm that here. Number 2. Now read this carefully. The unit for velocity is good. I gave you guys a little bit of a preview or a little bit of a warning. I said read it carefully. I didn't say that in my morning classes, and they all started with C. They just assumed the question was going to be asking about acceleration. So good. Velocity's units are meters per second, choice B. All right, and then question 3, the unit for acceleration is? Correct, meters per second squared, which is choice C. All right, let's talk about another scenario. If we have a horse galloping with a constant acceleration of positive 3 meters per second squared, which statement below is true? A, the horse's velocity doesn't change. B, the horse moves 3 meters every second. C, the horse's velocity increases 3 meters every second. Or D, the horse's velocity increases 3 meters per second every second. All right, good. I see more than half of you replying, and almost all of you now, and agreeing 100%. It is D. The horse's velocity is increasing 3 meters per second every second. All right, now let's try some math problems with this definition. Your velocity changes from 60 meters per second to the right to 100 meters per second to the right in 20 seconds. What is your average acceleration? All right, seeing a little more variety on this one, but mostly 2 meters per second or 2 meters per second squared. Carson, you were the first one I saw that actually put a plus sign on it. What was the reason you added the plus sign?
Because it had the plus on the last question.
Okay, good. Jilly, how about you? I saw you added it too. Any reason you can see why that plus sign is important?
To the right is positive.
Okay. And what about what about acceleration indicates or tells us that that's an important detail?
It's a vector.
Good. Since it's a vector, we do need to either with words or a sign indicate the direction. And so we would want to include that positive sign, or since this question said to the right and to the right, we could also just say 2 meters per second squared to the right. Generally speaking, with acceleration, we normally will just talk about it being positive or negative. By far, that's the most common way we'll think about it. It gets a bit confusing if we start using other directions for acceleration, and the more complicated scenarios we get into later, it'll become clear why word directions aren't quite as handy for acceleration, whereas the plus or minus sign is much nicer to deal with for most problems. But either way would be okay for a problem like this. All right, number 6, your velocity changes from 60 meters per second to the right to 20 meters per second to the right in 20 seconds. What is your average acceleration? All right, seeing most of you already putting an answer in, and 100% agreement so far. It is negative 2 meters per second squared. We take the final velocity of 20 minus the initial of 60, which gives us a change of negative 40. Time is a scalar, so it has no sign. So our negative 40 meters per second divided by 20 seconds gives us a negative 2 meters per second squared. And on that one, the sign probably makes more sense, or would be more likely you wouldn't forget it because it's negative. But even if it's in the positive direction, we need to use words or signs for vectors. Number 7, your velocity changes from 50 meters per second to the left to 10 meters per second to the right in 15 seconds. What is the average acceleration? All right, good. Seeing correct answers flowing through the chat. Our acceleration being change of velocity over change in time. Our initial is positive 10. We'll always assume that right is positive unless it's specifically stated otherwise. So the final, final velocity is positive 10. The initial is negative 50, but we're subtracting. So minus a negative means we add. So our delta V is 60 meters per second. And that happens at a 15-second time span. So it's a positive 4 meters per second squared acceleration. All right. We move on to the next one. We are going to begin to discover kinematics equation 1. And it's not technically like officially defined as 1. So like Newton's laws, there's Newton's first law, Newton's second law, Newton's third law, and they're specifically defined that way. These equations aren't really defined as 1, 2, 3, and 4. I just number them based on the order that we learn them. And we learn them in the same order that they're given on the AP formula list. And so when I just say use the first equation, I only am saying that not because it's technically called that in textbooks. It's just it's the first one you usually learn, and it's the first one on the list on the AP formula chart. So it is basically the definition of acceleration. So that's why we're learning it today. We've just defined acceleration, both verbally and with an equation. Now we're going to rewrite that into what is generally considered kinematics equation number 1. So let's break that down. We are again talking about motion at constant acceleration. So we're not having a changing acceleration. And we know acceleration is defined as change in velocity over change in time, where that delta symbol just means change in. So the first step we can take is one we've already seen on an earlier slide. We can recognize that delta V is just final velocity minus initial, and we can substitute that in for delta V. We can also recognize that it is very common to drop off the triangle for time, because as they show here, delta T is technically final time minus initial time. But if the initial time is 0, then the delta t is the same as the tf. So there's not any difference between the two if our starting time is 0. And normally when we measure time with a stopwatch, it will be. So that is one of the reasons why we often leave the triangle off the t. So that's familiar. We already have seen that. But now let's go ahead and solve it for VF. Let's just isolate the VF. So the first thing we would need to do is multiply both sides by t, which gives us a times t equals VF minus VO. And then I'm just going to rewrite that the other direction so that the VF minus VO is on the left, just to make it in a more traditional appearance. And then we need to add VO to both sides. And that would be our final equation. This is kinematics equation, the first one we're going to learn. VF equals VO plus AT. The final velocity is equal to the initial velocity plus the product of acceleration and time. Now, for this equation, a lot of students will often refer to this as VVAT. Okay, just looking at the letters, VVAT. And that's fine. It's just a nice, sometimes a student will say, oh, which equation did you use? And you say, oh, VVAT. And that is basically just the first one we learn. You know, you do have to remember where the equal sign goes and where the plus sign goes, but it's a nice little sort of acronym memory device. Occasionally, I will also refer to it as VVAT, just to remind you that this is the equation we're dealing with. So that is the first kinematics equation. And you can see it came from the equation for acceleration. I mean, this down here is the same as the definition of acceleration. We've just substituted some different variables and we've solved it for final velocity. But it's the same thing mathematically. We've derived this equation from the definition of acceleration. Now, the reason that I wanted to show you this, and I'll actually be deriving all the kinematics equations for you, some of them in multiple ways. Some of them will do both graphically and algebraically. And the reason is twofold. I think if you understand where these equations come from, and they're not just something you have to memorize or something that just seems like some genius just came up with it. If you recognize, no, it's not some math sorcery, it's just algebra, then you realize, oh, it's nothing that difficult. It's just math. It's just algebra. It's not even complicated math. And so I think that takes some of the mystery and some of the fear out of it. But the more important reason is on the AP exam, they always have questions in the free response part that ask you to derive equations. And they won't necessarily, in fact, they almost never ask you to derive one of these equations. They'll give you an equation like this and then give you some data and say, okay, integrate what you're learning in this data with this equation and create a new equation. And they want you to derive a new equation. And so we kind of start with these kinematics equations, teaching you how you can take equations and definitions and integrate them together to make new equations. And that hopefully will help you become more and more comfortable and more confident at those deriving of other equations when you take the exam in May. So a couple reasons why I like to show you how these equations are derived. I will not be asking you to derive VVAT, but I will at times be asking you to derive other equations from it. So I want you to get used to seeing this process. All right, the other thing that I want to mention, if you have not printed your College Board AP Physics equation sheet, I would suggest you do that. And let me just show you again where you can find it. And I want you to keep this VVAT in your mind for a second here. And let me show you the difference, the way this equation looks on this screen compared to on the AP formula sheet. So let's go to Axis. On Axis, when you get to the bulletin board page, if you scroll down, in the download section over here on the bottom right, you can see physics equation sheet right here. And if you look at the physics equation sheet, this first page has some constants, it has some unit symbols, some trig information, some metrics prefixes, and conventions that the exam follows. To be honest, most students look at this page very seldom. There's not a lot on this page that we use frequently. The other page, though, is where you're going to be looking at this page all the time. Starting in this unit, moving forward, we're going to be learning equation after equation after equation. And the one we just learned is this one up here in the top right-hand corner, right there at the top, or sorry, top left-hand corner, under mechanics. Vx equals Vxo plus Axt. So you may notice they've added a bunch of x's on this one compared to what we just looked at in our notes. Those x's are sort of unimportant. The reason that they've included them is there is an important concept that they're trying to emphasize, and that is that if we're thinking about the final velocity and the initial velocity and the acceleration, they have to all be in the same plane of motion. They have to all be in the x-axis, or they have to all be in the y-axis, or they have to all be in the z-axis. They can't be mixed. So if we're talking about the final x velocity, then we also have to be talking about the initial x velocity. It has to be in the same plane. Now, right now that may seem irrelevant, like why do we even need to worry about that? But in our next unit, when we get to projectile motion, then you're going to see why it's important. Actually, not the next unit, but the next part of this unit. So that x, it's not really important that you write those x's, but it is just important that you recall whenever you use these kinematics equations, the displacements, the velocities, the accelerations, they all have to be in the same plane for a single equation. If the object is moving in 2 different dimensions, you have to use a separate equation for each dimension. And like I said, we'll dig into that more later, but for now, just recognize that slight difference, that they like to include these little subscript x's. And again, you'll also see they did not put an f on the final velocity, they just call it v. Excuse me, that is also very common. All right. So I would encourage you to print that worksheet, print that handout, and keep it with you every time we take notes, every time you do homework, every time you do labs, every time you take a test. Well, when you take a test, I'll give you a fresh copy. You won't be able to use one you've written on. But in class, I would encourage you to actually just write on that equation sheet. Make notes to yourself, highlight things, circle things that are important. And you may have noticed on that first page, the whole bottom half almost was empty. It was blank. There will be quite a few times this semester and next where I'll teach you equations that aren't on the list. And that blank side, that open side on the front, is a great place to put the equations that are extra that they don't give you. Not that you could use them while you're taking the exam, but you have them all collected in a nice, neat place. By the end of the year, we'll probably have 20 or 30 equations that are not on that list, but that would help you on the test. And if you just one by one keep adding them every time I say, hey, this isn't on the list, but you should know it, just put it right there in that blank split space. And then at the end of the year, it's already there. It's already organized for you. I frequently have students at the end of the year say, hey, Mr. Webb, what are all those equations that you told us? And I'm like, there's so many of them. I don't have them memorized. So I mean, I have the equations memorized, but I don't have it memorized which ones you should know and which ones are on the list. And so I'm challenging you to, as I explain them as we go through the course, you take the responsibility to put them there or make another list. And I'll remind you the first time we get to one to do that. But I would use that. So the main point of emphasis today, print that thing. Keep it handy. All right. Let's go back to the notes. We're almost done, actually. All right. So let's just practice using this VVAT equation, this first kinematics equation in your tool belt. Starting from rest, you accelerate at positive 4 meters per second squared for 6 seconds. What's your final velocity? So once you figure it out, go ahead and put it in the chat.
Mr. Webb.
Mm-hmm.
So adding the plus sign, like, is it just like understood that if there's no plus sign, then it's just assumed positive? This is just to reiterate.
It's not assumed. If there's no plus or minus sign, then it may be assumed that you're just talking about the speed, not the velocity.
Okay.
Because they might think, oh, there's no sign, so it must be a scalar. And so
Right.
they may think it's just the velocity or just the speed. And
Okay, so for velocity, you really do need to put the plus.
yeah, for vectors, so
Okay.
displacement, velocity, and now acceleration. Either
Okay.
words or a sign. Yeah. Yeah, great question. So you'll see here, we've got an initial 0. I think all of you are getting it. Positive for 6 seconds. So our final velocity would be 24 meters per second in the positive direction. Good. All right, let's just do a few more here to wrap it up. You have an initial velocity of positive 5 meters per second. You then experience an acceleration of negative 1.5 meters per second squared for 4 seconds. What is your final velocity? Good. And this one, because it's negative, typically students won't forget to include that. Let's actually practice sig figs here for a couple seconds. And then, but before that, let me make another comment on Gavin's question about the signs. Not always, but often on the AP exam, the question will actually say, give the magnitude and direction of the velocity. So there's sometimes that little reminder. You need to have a word or a sign on it, but they don't always include that little reminder. So you do want to kind of get into the habit of thinking the 3 vectors that we use for now, velocity, displacement, and acceleration, that you've always think about, oh, that needs a sign or a word. But let's look at sig figs for this one. So they haven't really focused on them, but the 1.5 has 2. And then you can see up here in the question, it was actually 4.0. It wasn't just 4. So that also has 2. So what's 1.5 times 4?
6.
6. And with that multiplication step, the 1.5 has 2, the 4.0 has 2. So instead of just writing 6, we really should write it as 6.0 with 2 sig figs. And then this 5 technically was a 5.0 given, right? So 5.0 minus 6.0, what should this final answer be to reflect sig figs correctly?
Negative 1.0 meters per second.
Good. Yeah, we need that 0.0 added on to the way they've shown it here. And they frequently don't think about sig figs. They're just focused on teaching you the math and the substitution. But I would want to, every once in a while, keep practicing sig figs with you. All right. You have an initial velocity of negative 3 meters per second. You then experience an acceleration of positive 2.5 meters per second squared for 9 seconds. What is your final velocity? I'm seeing a few, mostly positives, a few negatives, and some with no sign. So we need to have a sign because velocity is a vector. The sign should be positive because we've got a negative initial velocity, but our acceleration is positive. Let's go ahead and do this one with sig figs too. This one's a little trickier, so this would be a good one to practice. So technically here, our final velocity is equal to negative 3.0 meters per second, right? Because they gave us a 0.0 in the problem. For 2.5, what's 2.5 times 9?
22.5.
Yeah, 22.5. But this 9 was really 9.0, right, up here? So if that has 2 sig figs and that has 2 sig figs, what do I need to round this to show 2 sig figs?
23 or is it 22?
5 makes us round up. Technically, there is a rule where if it's exactly 5, you can round to make it even. You could do that, I suppose. I typically just go with this normal rounding rules because College Board does. But there is an even odd rounding rule if you've learned that before. But I would do 23 here. And so we're going plus 23 meters per second. So in this step, we're doing multiplication, right? So multiplication means, okay, this has 2, this has 2, so this has to have 2 sig figs. Okay, we're thinking about sig figs. But in my last step, we're adding. So this goes to the tenths, this goes to the ones. So my answer can only go to the ones. So it should actually be 20 meters per second if we're thinking about sig figs. All right.
So if the College Board asked that, they wouldn't accept plus 19.5, they'd accept plus 20 point.
So what they would do, it depends. So some questions, the sig figs is one of the points. Sometimes it's not. And so if it was one of the points, you would lose 1 point. You wouldn't miss the whole question. Sometimes in the rubric it counts, sometimes it doesn't. And there's no way to know ahead of time. It's not included in the question. So I just always challenge students, try to use sig figs all the time because you never know when it might count. Any other questions? It's a little trickier one because we've got a multiplication step that gives us one number of sig figs, and then we've got an addition step that gives us sig figs in a little bit different way. And this problem requires both steps, both rules. All right. Just 2 more, then we'll just wrap it up with these quick. How much time does it take to come to rest if your initial velocity is 5 meters per second, positive 5 meters per second, and your acceleration is negative 2 meters per second squared? All right. Do we need a plus or minus on this one? Why not?
Time is a scalar.
Yeah, good. Time is not a vector, time is a scalar. So another comment about College Board, they require you to show work, just like I've mentioned before that I require you to show work. So the work that they require is you have to show an equation. So they recommend you show the original equation, which they've done. Then you do the algebra to solve the equation for the required variable. Then you substitute, then you solve. So this curriculum, one of the reasons I like it is they follow this pretty consistently to remind you this is the preferred College Board format. This is what they suggest you do. Equation, rewrite the equation, substitute, solve. What they require in most rubrics is an equation, whether you write it as the normal VVAT or whether you already have solved it for T, at least in one form or the other, you need to have an equation. Then they also require the substitution, whether you substitute it into the original or whether you substitute it into the modified, doesn't matter, but they do require those 2 steps in almost every question, the equation step and the substitution step. So now that we're getting into more and more complicated equations, make sure you get into that habit of always writing your equation, then substitute, then solve. All right, and actually, I'll see if I can fix that. I don't know if it'll let me edit that, but there really shouldn't be a positive there because time's not a vector. All right, last one. An object accelerates at a rate of positive 3 meters per second squared for 6 seconds until it reaches a velocity of positive 20 meters per second. What was its initial velocity? Good. And this one is a velocity. Velocity is a vector. So for this one, we do need the positive to indicate that it was moving at 2 meters per second in the positive direction initially. And there's the substitution. So original equation, rewrote it, substituted, solved. All right, any questions from today? That's the end of the lesson for learning content. All right, I'm going to walk you through the 3 assignments. There's one that's due this Thursday, one that's due next Monday, one that's due next Thursday. But for a couple of them, I think having more time and being able to sort of just do the work when you have the best time available is better. If I wait and don't tell you Thursday and you have a lot of time this Wednesday, you've lost opportunity to get some of it done. So I want to give all 3 of them to you ahead of time so you can kind of gauge and evaluate your own schedule better. So on Axis, let's just take a quick look at the calendar here so we can see what's coming up. I like to look at the calendar view personally. So here's October so far. This Thursday, the Moving Man Lab is due. Next Monday, the summary sheet activity is due. And next Thursday, the positive physics acceleration is due. So those are the 3 assignments. I won't be giving you additional assignments during this time frame. We'll be doing other work in class at times, working on some of the other worksheets just for in-class practice. But these will be the only assignments you'll be given. And so I'm going to actually talk through the process for each one in backwards order. That way I'm finishing with the one that's due more near to now. So it'll be the freshest in your mind. So the one that's due the furthest down the road is the positive physics. And just another reminder, anytime you click on these, it gives you some feedback. It looks a little bit different on your screen than mine, but you should still be able to see this information. And you can see this time it says, complete the assessment. So last time we used positive physics, you did the work. This time you're doing the assessment, and I'll show you that here in just a minute. And then it also tells you your grade will be the average between the original and correction scores you earn. Okay, so there's some good things there. And then it gives you some directions. Submit a screenshot of your final score. All right, and you'll notice this type is a quiz. All right, but this quiz is open book, on your own pace. You just have to have it done by 11:59 p.m. on next Thursday. All right, so it's a kind of a different kind of a quiz. You're not limited to doing it during class. Now let's go back to positive physics and remind you of a few things. And let me show you a couple things about the assessment that could be helpful for you that since this is the first time doing an assessment, you may not know. So let me go do one of my fake student accounts here. All right. So when you go in, I think it'll actually take you to the assessment automatically, but you can see there's the 3 tabs here. If you're on the work tab, all the headings are blue. If you're on the extra practice, it's darker blue. And if you're on the assessment, it's black. Okay, so make sure you recognize that, sorry, some of my neighbors are having some trouble, it sounds like, with their car. If you get to the assessment tab, you'll notice in this column, total problems, it says we've got 0 from the inquiry section, 2 from the motion charts, 4 from vocab, 3 from embedded math, 1, 1, 1 through. So you can see where the questions are coming from. And if you click on anywhere in this score column, that's when it takes you to the actual assessment. All right. Now I was filling in some of this to show earlier to another class, so we'll do something similar for you guys. But when you open up the assessment, you'll see there's 15 questions. So it's not a very long assessment, but you do need to, I want to give you time so you can go back and forth and use the work section to help yourself. So notice this is a problem with some cars, and it says a car initially traveling at 10 gains speed at a rate of 2 meters per second for 4 seconds. And then question 2 has some bicyclists. A bicyclist initially at rest speeds up with the uniform acceleration of 3 meters per second squared for 4 seconds. So keep that in mind. Now let's go back to the dashboard and let's click. Remember here, these 2 questions, these are in order. So the first 2 questions are from the motion charts part of the work. If you go back to work and click on the motion charts. There's a video to help you. And there are 4 questions here. This first question is the same as that second assessment question, just with different numbers. And then if you scroll forward, this is the same as that car question, but just with different numbers. So you can practice them here, check your work, make sure you know how to do it, and then go back to the assessment and complete it. Now, as you complete it, you can see that I'm just going to fill in a few of these for you guys to see how it works. I won't take the time to calculate this, but the units for acceleration should be meters per second squared. The units for time should be seconds. That must be underneath that. There we go. Units for velocity, meters per second, and units for displacement should be meters. So even though I'm not done, if I click check answers, it'll show me for the ones that I've filled in whether they're right or not. Okay. And then I can say, I'm just going to throw something in here. Let's say it's 2. I have no idea. Check answers. Probably wrong. Okay, so it's wrong. Okay, now I can't go back and change it like you can in the work section. It's fixed. Okay, so once you click check answers, that's saved for good. Okay, now let's say though that I'm a little confused. I got this wrong, so I want to go back to the work section and look this up. So I go back to the work section, find that question, practice it here, get it figured out, go back to the assessment, and then finish it. And you can see the works that I checked are all saved. Okay, now, if you don't click check answers, it doesn't save your work. So when you come back, it'll all be blank, and probably these numbers will be different. Okay, so you need to save your work by checking answers before you go back and forth. And you need to click check answers for every question, all 15. If you forget to click check answers, it doesn't save it. And so then when you go on and come back later, it'll all be gone and you'll have to redo it. So make sure you click check answers to save your work for every question. All 15 questions, you need to click check answers. Now, after you've done all 15, then you're going to click finalize. Okay, finalize means you're finally done with the whole thing, not just this question. Like you're done with the whole quiz. So you don't want to click finalize until you've completed the whole quiz. Okay, once you've completed the whole quiz, then when you click finalize, then you can go back and correct these red ones. But it won't let you correct them until you've finished the whole quiz and clicked finalize first. Once you're done, then you'll see right now Larry Bird's grade is not looking too good. He's got a 27% here on this section. So his overall grade is 4% because he's only answered part of 2 questions out of 15. And his corrections percent still at 4 because until he finalizes it, he can't go back and make any corrections. But what I'll be doing is looking at these 2 percentages and averaging them. And that will be your score. Okay, so hopefully that explains how it works. Any questions? If you forget some of those steps, if you come back to the bulletin board page over here in these downloads, I typed out directions for positive physics right here, and it sort of talks you through a lot of those steps. So if you need that, you can come back to this directions for positive physics to help you. All right, the next assignment on the calendar is the summary sheet. Okay, and it's due next Monday. The summary sheet just tells you, if you click on it, it recommends you try to complete the first 3 pages by Thursday or Friday, and then complete the last 2 pages by Monday or Tuesday, depending on sections. This is just a suggested pacing guide, just to help make sure you don't try to do it all in one sitting. It's a homework assignment. It's basically just a worksheet, so it's not too complicated for you to figure out. You'll find it in topics. So go to topics. We're now in unit 3, so you need to come down here to unit 3, constant acceleration model. And you can see it right here, summary sheet, constant acceleration worksheet. And then there's a webcast. It's actually a video, about a 15-minute video. For those of you that may have known Miss Turk, Amanda Turk, she used to teach at Oaks a few years ago. She actually made this screencast, and we used the same curriculum. So I asked her if I could borrow it, and she said sure. So it might actually be good for you to hear it explained from a different teacher's perspective. I mean, we pretty much have the same perspective, but just the way she phrases it might be a little different. So there's a screencast, there's PDF slides and PowerPoint slides. So you can use these 3 resources to help you complete the worksheet. And that's due next Monday. The one that's due this week is Moving Man. And you can see right here, there's a Moving Man simulation. If you click on it, it's going to take you to this PhET simulation. And probably most of you have used PhET simulations before. And then right underneath the link to the simulation, there's the doc version and the PDF version. So you can choose which format you like. I've opened up the PDF form here. And you can see in the directions, there's also a link to the PhET there as well. The first part, constant velocity, is basically what you just took a test over. So this should be a review, this first part. You do the directions, read what it says, fill in the table, draw some graphs, answer some questions. Pretty straightforward. Then you get into part 2, which is now with constant acceleration, which is the new stuff we're learning. Tells you the settings, asks you some questions, you fill in the table, you fill in the graphs, you answer some questions, and you're good to go. All right, so that is the one that's actually due Thursday of the 3 assignments, the Moving Man. So summary sheet and Moving Man you can find right here in topics. Positive physics, obviously you'll need to go to the Positive Physics website. Any questions about the assignments over the next 2 weeks? The Moving Man is the only one due this week, but I just wanted to get you some knowledge about what's coming up. So if you have some spare time, especially on Wednesday, maybe you could start working ahead on some things instead of waiting until it's closer to the due date. If you have further questions, you're welcome to stick around online.